Data is the lifeblood of every modern organization, especially in industries like healthcare, where every decision can impact lives. But here's the challenge: as data grows, so does the complexity of managing it. Today, I'm here to share the story of a Fortune 500 healthcare provider that turned its chaotic data ecosystem into a seamless, scalable powerhouse and achieved a 30% boost in productivity in the process. This isn't just a story of transformation, it's a masterclass in how modern cloud technologies like Azure and Databricks can simplify complexity, reduce the costs, and enable innovation. Let's dive in and see how they did it. But first, let's take a closer look at the challenges they were facing. Let's walk through the key challenges they faced. There are five main issues to highlight. First, they were dealing with unstructured data from 12 different data sources across 7 lines of business. The data was fragmented, inconsistent, and hard to manage. But that was only part of the problem. They also had over 47,000 job configurations, 90 plus projects, and 2,000 workflows. Imagine the complexity of keeping all of that running smoothly. It was overwhelming. And then there was the issue of costs. Legacy systems like Ab Initio and Netezza were expensive to maintain. Worse, they couldn't scale to handle the growing data needs of the organization. The challenges didn't stop just there. Every time they needed to add a new data source or update a process, it took weeks. This meant critical insights were delayed and the time was wasted. Finally, let's talk about the data quality issues. Inconsistent systems led to unreliable data, which made it hard for decision makers to trust the reports they were getting. So, these five challenges: unstructured data, complexity, high costs, slow processes, and poor data quality made it clear they needed a better system. So, how did they overcome this? Let's explore the solution. The turning point came when they embraced a modern cloud based data architecture powered by Azure and Databricks. They didn't just fix what was broken, they reimagined the system to be smarter, faster, and more cost efficient. Let's break it down step by step, starting with the data ingestion. Step 1 was centralizing their data using Azure Data Factory or ADF. Think of ADF as the ultimate data courier. It connects, extracts, and delivers data where it needs to go. Here's what ADF brought to the table. First, it connected on-prem databases, legacy systems, APIs, and flat files into a unified pipeline. This eliminated silos and brought everything together. Second, it saved time and reduced errors. ADF automated data workflows, removing the need for manual intervention. This made processes faster and more reliable. Finally, it supported different types of data, whether it was batch processing or real time streaming. ADF handled it all, making the system future ready. By solving these three challenges: connectivity, automation, and flexibility, ADF laid the foundation for everything else. Once the data was ingested, the next step was to process it. After centralizing the data, they used Databricks Delta tables to process it efficiently. This is where the medallion architecture comes into play. Let me break it down for you. The bronze layer. First, the bronze layer stored raw data exactly as it came in. This ensured they could always trace back to the original source. Next, they needed to clean and enrich the data. The silver layer cleaned and enriched the data, making it analytics ready for teams to use. And finally, they needed to create business ready outputs. The gold layer transformed the data into formats optimized for dashboards and reports. This layered approach, bronze, silver, and gold, ensured the data pipelines were structured and reliable. But what made the system truly smart was automation. Let's talk about it. They introduced a metadata driven ingestion framework to make the system intelligent and adaptable. Here's how it worked. Instead of hard coding workflows, they use metadata rules. This allowed the system to adjust automatically for new data sources. Consistency was also critical. So every data source followed the same transformation rules, reducing errors and ensuring high quality outputs. And finally, the automation made everything faster. The entire process from ingestion to transformation was automated, eliminating repetitive tasks and saving time. This framework made the system dynamic, scalable, and efficient. With automation in place, they now needed to make this data actionable. Let's see how they did that. To turn their data into actionable insights, they use Azure Synapse Analytics and Power BI. Let me explain how this worked. Synapse stored the enriched data from the gold layer of Delta tables, ensuring it was ready for analysis. Next, they needed fast and efficient queries. With Synapse's dedicated SQL pools, they could run complex queries in seconds, supporting real time analytics. And finally, they needed to present this data effectively. Using Power BI, they created dynamic dashboards that allowed business teams to track the KPIs, spot trends, and make confident decisions. Together, Synapse and Power BI bridge the gap between data processing and actionable insights. Now let's talk about why they chose Azure for their transformation. So Azure was the perfect choice for three key reasons. First, being seamless integration. It connected their on-prem systems to the cloud without disruptions. It also offered powerful tools for analytics. Also, Azure's integration with Databricks and Synapse provided cutting-edge tools for big data processing. And finally, it delivered value for money. Azure's pay-as-you-go model ensured they only paid for what they used, maximizing the ROI. These three factors made Azure a strategic partner, not just a provider. Finally, let's look at the results of this incredible journey. Here's what they achieved with their new system: a 30% productivity boost, automation and faster pipelines save time and resources. They also improved the data quality. Consistent pipelines delivered reliable and accurate reports. And finally, they also saved a lot of money in the process. Retiring legacy systems and optimizing storage reduced costs significantly. Scalability was another key result. The platform could handle new data and growing needs more effortlessly. And finally, they gained better insights. With Power BI, they had real time dashboards to guide decisions. This just wasn't an upgrade, it was a complex transformation. Now, let's talk about how you can achieve the same. This story isn't just about one organization, it's about what's possible for anyone. At Data Engineering Academy, we'll teach you how to use tools like Azure Synapse, Data Factory, and Databricks, build powerful data platforms, create actionable insights with Power BI. So, are you ready to transform data, transform careers, and transform lives? Let's get started today. Transform your future with us. Welcome to this customer case study on AWS Glue migration to Snowflake. Why are we discussing this today? So, in today's fast paced world, businesses rely on real time data processing to make critical decisions. But what happens when your ETL pipeline becomes slow, expensive, and complex? That's exactly what happened to a leading enterprise that depended on AWS Glue for data processing. They found a better way by migrating to Snowflake. In this case study, we'll explore why AWS Glue was their initial choice, the challenges they faced as data volumes grew, how Snowflake helped them achieve better performance and cost efficiency. By leveraging Snowflake's cloud native capabilities, this company achieved significant cost savings, faster data processing, a simplified, more scalable architecture. Let's dive deeper into this journey and understand what made Snowflake the right choice. Before we dive into the migration story, let's take a moment to understand AWS Glue. the ETL service that was originally used in our case study. So, what is AWS Glue? AWS Glue is a serverless data integration service that helps business extract, transform, and load data across different data sources. Think of AWS Glue as the middleman between raw data and analytics. It consists of four major components. First being the AWS Glue crawler, which is nothing but the detective. Imagine you receive a pile of messy documents and need to figure out what's inside before organizing them. That's exactly what AWS Glue crawler does. It scans raw data stored in places like Amazon S3 or relational databases. It identifies the data type, schema, and structure. It automatically creates the metadata, so Glue knows how to process the data. Once the crawler finishes, all this information is stored in the AWS Glue data catalog. So if the Glue crawler is the detective, then Glue data catalog is the library where all the findings are stored. So it acts as a central repository for metadata. It keeps track of table names, column structures, and file formats. It allows different AWS services like Athena, Redshift, and Glue itself to easily find and use the data. With this catalog in place, we now know what our data looks like and where it lives. But we still need to process and clean it. That's where glue jobs come into the picture. So now we need to extract, clean, and load the data into a target system. So this is done using AWS Glue jobs. So Glue jobs use PySpark or Scala scripts to process large data sets. They apply transformations such as cleaning, deduping, and structuring data. Once transformed, the data is moved into a final storage location for reporting. But how do the glue jobs know when to run? That's where triggers come into play. So AWS triggers are nothing but the automation engine. AWS Glue triggers help automate workflows. Triggers automatically kick off the ETL process when certain conditions are met. There are three types of triggers. First is on demand. So on demand triggers runs manually when needed. Then we have event driven, starts when new data arrives in S3. We have scheduled triggers. It runs at a fixed time. Example, a job can run every night at 2 a.m. So with crawlers detecting data, the data catalog storing the metadata, jobs transforming the data, and triggers automating the process, AWS Glue offers a complete serverless ETL solution. Now that we understand AWS Glue, let's look at how this company initially set up their data pipeline. Let's take a look at the previous architecture used by our case study company before migrating to Snowflake. The company relied on AWS Glue for ETL, extract, transform, load processing, but as we'll see, this setup had some serious challenges. Let's break it down step by step. The first step starts with data ingestion. Raw data lands into Amazon S3. The journey starts with raw data files arriving in an Amazon S3 bucket. These files include customer orders, payment transactions, shipping, and logistic records. This raw data is unstructured and must go through multiple processing steps before it can be used for analytics. In the step 2, AWS Lambda detects new files and triggers the ETL. As soon as new data lands in the S3 source bucket, an AWS Lambda function is triggered. Think of Lambda as an event driven automation tool. It detects new files and informs AWS Glue that processing needs to begin. This ensures automation so that the data processing starts as soon as the new files arrive. Step 3, we have the AWS Glue crawler. It scans and registers the metadata. Before we can process the data, AWS Glue needs to understand its structure. That's where the Glue crawler comes in. It scans the raw data and detects column names, data types, and formats. It then stores all this metadata into an AWS Glue data catalog. The Glue data catalog acts like a central metadata store, helping Glue jobs know what the data looks like before processing it. Now we are ready to move the files into a more structured format before transformation. The step 4, Data is moved into Amazon S3 named file bucket. At this stage, the raw files are moved into a specialized Amazon S3 named file bucket. Why is this step necessary? It provides a staging area before AWS Glue performs the transformations. It organizes and standardizes file formats, file names, making processing more efficient. It acts as an intermediate storage layer to keep things more structured. Th- These are the key steps before AWS Glue jobs run. The files must be properly structured. Next, we have the AWS Glue job. So that runs the ETL on the data. Once the files are structured in the named file bucket, an AWS Glue job starts processing them. The AWS Glue job follows a three-step ETL process. First being extract, it reads the structured data from the S3 name file bucket. It then transforms it, cleans it, formats it, and applies business logic using PySpark scripts. And finally, it's the load process where it moves the transformed data into the final processed S3 bucket. After the AWS Glue job finishes the processing, the cleaned and structured data is stored in another S3 bucket. The final S3 bucket serves as the data source for BI tools like Amazon Athena, Power BI, or Tableau. Now, analysts can finally query and generate reports from this processed data. Now, when we think of the challenges with this setup, although this setup kind of worked for the customer, but it had the following major challenges associated with it. The first being high operational overhead. So the engineers constantly had to tune the glue jobs and manage multiple components. It also led to delayed data processing because Glue operated in a batch mode, data wasn't available in real time. And as you can see, there were too many intermediate steps. Managing three different S3 buckets, raw, named, and final, added unnecessary complexity. Also, AWS Glue struggled to process data as volumes grew to 500 GB per day. Because of these challenges, the company decided to look for a better, faster, and a more cost efficient solution, which led them to migrate to Snowflake. So, now let's walk through their new architecture and see how it transformed their data pipelines. So, why Snowflake? Uh, Snowflake was chosen because it offers seamless integration with AWS services. It results in faster data processing and it had lower operational complexity. So, at the heart of this migration was the Snowflake's powerful copy into command. So, what does this do? It allows bulk historical data loading from Amazon S3 into Snowflake. It's optimized for fast ingestion and scalability. This approach provided a much simpler and a cost-effective ETL process compared to AWS Glue. Next, we also have the Snowpipe, which is the real-time data loader. But as you can see, historical data is just one part of the story. To enable real-time data ingestion, the company implemented Snowpipe, Snowflake's automated data ingestion service. Here's how it works. Step 1. A new file is uploaded into an S3 bucket. Step 2. An event notification is triggered. Step 3. The file is staged in Snowflake's external stage. Snowpipe automatically ingests this file into Snowflake's target table. This means that as soon as the data lands in S3, Snowpipe loads it into Snowflake, providing a near real-time data availability. Here's what the new data architecture looks like after migrating to Snowflake. So as you can see in the first step, we have data sources like transactional databases, weblogs, and third-party data. So they send in the data to the S3 bucket. For historical data, Snowflake uses the copy into command. For real-time data, Snowpipe automatically ingests the data as they arrive. Data is transformed inside the Snowflake using SQL-based processing, eliminating the need for complex PySpark scripts. And finally, the processed data is available for business intelligence and analytics, marketing and finance teams, machine learning, and data science use cases. This migration made the company's data pipeline simpler, faster, and fully automated. By migrating from AWS Glue to Snowflake, this company unlocked major benefits. First, it had fully automated workflows, no more manual glue job tuning, real-time data availability. Thanks to Snowpipe, data was available immediately instead of waiting for batch jobs. It also resulted in significant cost savings. Snowflake's pay-per-second pricing model reduced unnecessary compute costs, and also it simplified the architecture. No need for multiple S3 buckets, glue triggers, or Lambda functions. With Snowflake, the company gained a high performance, low maintenance, and a cost efficient data platform. By eliminating AWS Glue's complexity and replacing it with SQL-based transformations and automated ingestion, this company successfully modernized its data pipeline. If you found this insightful, stay tuned for more cloud architecture deep dives. Thanks for watching. Thank you. Hello everyone. Have you ever worked with a system that felt like it was holding you back? If that sounds familiar, you're not alone. Today, I'm sharing the story of a global retailer operating across these 3,000 stores in 40 countries. For over 15 years, their enterprise data warehouse served as the backbone of their operations, but as the business grew, the system started to show its limitations. Instead of patching up an aging system, they made a bold decision to migrate to Azure Databricks. This wasn't just an upgrade, it was a transformation that unlocked scalability, real time insights, and advanced analytics. In this session, we'll explore their journey from the legacy system they started with and the challenges they faced to the cutting edge Azure Databricks architecture they implemented and the results they achieved. By the end, we'll have a clear roadmap for building scalable, future ready data systems. Let's dive in. To understand their transformation, let's look at their legacy architecture. Their legacy data platform was centered around a SQL Server 2014 enterprise data warehouse. This system had several components working together to manage their global operations. As you can see, ATG for e-commerce. So this platform managed online transactions, pulling data from websites, applications, and marketplaces. It also handled promotions tailored to different regions. While functional, it struggled to manage the increasing volume of online transactions. While the ATG supported the online operations, in-store transactions were handled by another system called POS, commonly referred to as point of sale. This system ran on a DB2 mainframe and processed transactions from thousands of stores. It supported loyalty programs, promotions, and order management. However, it was rigid, making integration with modern tools a challenge. Data from these systems needed to be processed and loaded into the warehouse. Then we can see ETL with IBM Data Stage. So IBM Data Stage handled the extraction, transformation, and loading of data into the enterprise data warehouse. However, the ETL process was slow and inflexible, requiring custom development for every new data source. The heart of the system was their enterprise data warehouse. The Enterprise Data Warehouse, or EDW, was built on SQL Server 2014. This was where all the data was aggregated and analyzed. While it supported basic reporting, it struggled with the scalability and processing speed. Finally, let's look at how the data was consumed. So, BI tools like Cognos and Tableau were used. So, these tools provided reports for managers and executives. However, delayed data processing often meant insights were outdated by the time they were available. This architecture worked for years but wasn't built to handle the demands of a rapidly growing retail business. Now that we have explored their foundation, let's move on to the challenges they faced as the business scaled. As their operations expanded, the limitations of the legacy system became apparent. Let me explain the key challenges they encountered. The first being scalability issues. Their on premise servers were reaching capacity. Scaling up meant buying new hardware, a slow, expensive process that did not provide enough flexibility. Alongside scalability, processing speed was another issue. Batch jobs took hours to complete. This delay meant reports and insights weren't available in real time, which is crucial for retail decision making. Data integration also posed a significant challenge. They had data coming in from POS systems, e commerce platforms, and IoT devices, but integrating these sources required extensive custom development, creating bottlenecks. Another major issue was their inability to access historical data. If data wasn't extracted and stored immediately, it was lost. This made long term trend analysis impossible and limited their ability to generate new reports. Finally, their system documentation was also outdated. Over 15 years, system changes weren't consistently documented. This made troubleshooting and updates slow and a frustrating process. So these challenges made it clear that their system needed a complete overhaul. So how did they solve these problems? Let's explore their new Azure Databricks architecture. The migration to Azure Databricks introduced a cutting-edge architecture built for scalability, efficiency, and real-time analytics. At the heart of this transformation was the medallion architecture, which organizes the data into three distinct layers. Firstly, the bronze layer. This layer stores raw, unprocessed data exactly as it arrives from sources like Kafka, APIs, and IoT devices. For example, point of sale transactions and customer behavior data are ingested here in their original data formats. By preserving raw data, the bronze layer ensures nothing is lost, solving the problem of historical data access. After the raw data is stored, it moves to the next stage for processing, that is, the silver layer. In this layer, the data is cleaned, transformed, and normalized. For instance, sales data from different regions is standardized into consistent schema and duplicate records are removed. This structured data is ready for analytics and reporting. So, finally, the data is refined for business use case in the gold layer. So the gold layer, as you can see, aggregates and summarizes the data for BI. For example, sales data is grouped by time periods, regions, and product categories to generate actionable insights. This layer powers the dashboards, predictive models, and decision making tools. But this architecture doesn't stop at the data storage, it is powered by automation and real time processing. As you can see from the diagram, uh, workflow orchestration was done with Azure Data Factory. So Azure Data Factory automates the flow of data through these layers, ensuring consistency and efficiency. For instance, transaction data from Kafka streams is ingested every 15 minutes and processed into the silver and gold layers. Real-time analytics also plays a critical role in this architecture. For real-time processing, we used Spark on Databricks. So Spark enables real-time data processing, replacing traditional batch jobs. For example, sales and traffic data can be combined in minutes to evaluate the effectiveness of promotions in real time. So once the data is processed, it is ready for business intelligence tools. So we also had seamless integration with BI tools. So tools like Tableau and Looker provide real-time dashboards tailored for to ensure data accuracy. The system includes a robust validation framework. A custom data validation framework validates the data at every stage, checking for schema mismatches, missing data, and inconsistencies. Lastly, system updates are streamlined through automation. So Azure DevOps was used for CI/CD. Azure DevOps automates pipeline developments, ensuring seamless updates without disrupting operations. So this architecture addressed every challenge they faced transforming their operations. Now let's connect this architecture to the problems it solved. The new architecture resolved their challenges in several ways. Scalability. So Azure Databricks scales dynamically, removing the limitations of on-prem servers. Processing speed also saw a significant improvement. Real-time Spark pipelines replaced the slow batch jobs, delivering insights instantly. Integration became seamless as well. Azure Data Factory's automated workflows simplified the ingestion of diverse data sources. The bronze layer also addressed historical data issues. So, uh, in terms of access to the historical data, raw data was preserved, ensuring nothing was lost for future analysis. Lastly, the system management was also greatly improved. CI/CD pipelines and automation reduced the manual effort and eliminated inefficiencies. So, in terms of quantifiable impacts for implementing this solution, the results were incredible. So, it led to a 30% faster processing. So, real time pipeline saved hours every day. This also resulted in improved data access. Historical data was preserved and easily accessible. Seamless scalability was another benefit. Resources scaled dynamically to meet the growing needs. Uh, this implementation also led to enhanced reporting capabilities for the company. So, dashboards provided real time and actionable insights. And finally, the infrastructure costs were reduced by 40%. So, this migration highlights three critical lessons. Scalability is essential. Build systems that grow with your business. Preserve raw data. The bronze layer ensures flexibility for future analytics. Automate workflows. Tools like ADF save time and reduce errors. Now, here's how you can take the first step. At Data Engineering Academy, we teach you how to design scalable architectures using Azure Databricks, master tools like Spark and Azure Data Factory, lead successful cloud migrations with confidence. Hello, everyone, and welcome to this session where we'll explore how a media and entertainment customer is modernizing its data architecture using cloud services. If you're new to cloud computing or data architecture, don't worry, I'll explain everything in detail. By the end of this video, you'll have a solid understanding of how data flows in a cloud environment, how modern tools like AWS and Snowflake are used, and why this is important for businesses. Let's get started. So let's start with the business context. The media and entertainment customer wants to modernize its data architecture. But what does that mean? So, in simple terms, they want to move away from old complex systems and use simpler, more efficient cloud services. But why is this important? Well, in today's world, data is one of the most valuable assets for any business. However, if the data is scattered across different systems, it becomes hard to access, analyze, and use effectively. That's why the customer wants to create a single source of truth, a central place where all the data is stored and managed. This will help different teams access and use the data more easily, and it will also allow for better data sharing across the organization. Next, let's talk about the legacy state. So, this is the old system that the customer is currently using. The legacy system has several challenges that make it difficult to manage data effectively. Let's break down these challenges. First, complex data pipelines. So the customer is using AWS Glue, which is a tool for moving and transforming data. However, the setup is complicated. Imagine trying to build a highway system with too many twists and turns. It becomes hard to navigate. That's what exactly happening. The data pipelines are overly complex, making it difficult to move data from one place to another. Next, there is limited collaboration. Different teams aren't working together effectively because there is no central place to store and share the data. Think of it like a library where books are scattered all over the place. It is hard to find what you need. Similarly, without a unified database, teams struggle to access the data that they need. There is no unified database, so there is no single place where all customer data is stored. This makes it hard to get a complete view of customer interactions. For example, if a customer interacts with the company through multiple channels like social media, email, and in store purchases, it's difficult to track all those interactions in one place. And finally, they have fixed ingestion patterns. The company only has certain ingestion patterns that are supported in the current architecture. So in case a new ingestion pattern or a data source needs to be onboarded, it again takes weeks or even months. So these were the challenges that the customer was currently facing. So in the future state, the customer wants to solve these problems by implementing several key changes. Let's go through them one by one. The first is the customer wants to implement data contracts. So these are nothing but the agreements between data producers, the team that create the data, and data consumers, the teams that use the data. So data contracts define how data should be structured, formatted, and shared. Think of it like a contract between a landlord and a tenant. It sets clear rules for how things should work. Data contracts ensure that the data is of high quality and trusted, and they help prevent misunderstandings between the teams. Then they want to implement core data products. So these are the data sets that are designed by the platform team in consultation with the business. Think of core data products as the foundation of the house. They provide essential structure that everything else is built on. These data sets are carefully curated and optimized for use across the organization. And then there are derived data products. So these are the data sets that are created from core data but tailored for specific business needs. For example, the marketing team might create a derived data set that focuses on customer behavior, while the finance team might create a data set that focuses on revenue. Derived data products allow teams to customize the data to meet their specific needs. And finally, the customer wants to have improved collaboration across teams. So the customer wants to improve collaboration between the engineering and governance teams. They're using tools like Alation for metadata management and Open Telemetry for data observability. Metadata management is like creating an index for a library. It helps teams find the data they need quickly. Data observability is like having a dashboard in your car. So it gives you real time information about how the system is performing. So, with that context being set, let's look at the legacy architecture in more detail. So, in the old system, data comes in from different sources like Oracle, MariaDB, and streaming sources. These sources could be anything from customer databases to real time data feeds from social media. The data is extracted using AWS Glue, which is a tool for moving and transforming data. So AWS Glue is like a conveyor belt that takes data from one place and moves it to another place. However, in the legacy system, this process is complicated and it involves custom Python scripts. So once the data is extracted, it is loaded into an S3 bucket. So S3 is the cloud storage service provided by AWS. Think of it as a giant storage locker in the cloud. The data is stored in different folders within the S3 bucket depending on its source. From there, the data is transformed and moved into different layers. So as you can see, we have layers like rawest, syndicated, and curated. Snowflake is being used as a cloud-based data warehouse. So the rawest layer is where the raw data is stored. The syndicated layer is where the data is cleaned, and the gold layer is where the data is fully aggregated or summarized for the business use. So this is how the legacy architecture looked like. Let's look at the future state architecture. In the future state, the process is more streamlined and efficient. Let's break it down step by step. Let me zoom in a bit. So for the batch data sources, for data that comes in batches like daily sales data, the process starts with DMS, which is Amazon's data migration service, which extracts the data from sources like Oracle, MariaDB, etc. So the data is then sent to Kinesis stream, which is like a river of data flowing in real time. From there, it goes through a Lambda function, which is like a piece of code that processes the data. And finally, the data is sent to Kinesis Firehose, which loads the data into an S3 bucket. For streaming sources, for real-time data streaming like social media feeds, the process is similar, but it skips the DMS step. So the data goes directly from the source to Kinesis stream, then to Lambda, and finally into S3. So once the data is in S3, it's loaded into Snowflake using Snowpipe, as you can see it here, which is a tool for continuous data loading. Snowpipe automatically loads the new data into Snowflake as soon as it arrives in S3 with with a latency of just 1 minute. So the data then goes through different layers of transformation using dbt and UC4 as the scheduler. So dbt is used to clean, deduplicate, and version the data, while UC4 ensures the transformations happen on a schedule. So this is how the future architecture looks like. Now let's dive into the detailed data model. So data is organized into different layers known as the medallion architecture. Think of it Think of this architecture like a factory assembly line where raw materials data are refined step by step until they become a finished product. So we have the landing layer. So this is where raw data first arrives, like the receiving dock of a factory, where raw materials are unloaded. The data here is in its original form, straight from the source. Next, we have the bronze layer. Here the data is cleaned and flattened. Cleaning means removing errors or inconsistencies, and flattening means converting complex data structures like JSON into simpler format. This is like taking raw materials and cleaning them up so that they are ready for processing. Next, we have the silver layer. So here the data is deduped and versioned. Deduped or deduplication means removing duplicate records, and versioning means keeping track of changes to the data over time. This is like refining the materials further to ensure they are of high quality. And then we have the gold layer. So this is the final layer where data is fully curated and ready for business use. It's like the finished product coming off the assembly line, ready to be shipped to the customers. So this is how the detailed data model works in action. So data is organized through your medallion layer system. These different stages represent the different levels of data curation: landing, bronze, silver, and gold. UC4 is used as a scheduler, and DBT is used to perform the transformations. So in terms of how the flow looks like from bronze to silver to gold, so data based on batch ingestion pattern or streaming ingestion pattern will be loaded into Snowflake landing layer using Snowpipe. Then DBT models are generated using Python scripts to load the data into bronze. The conceptual data models and the entity relation diagrams are developed by the data modelers, and then DBT models are created using the Python scripts. And finally, the curation happens in the gold layer. So, using DBT, summarizations and aggregations are done on the gold layer. So, the client or the customer here implemented data contracts. What are data contracts? So data contract is an agreement between the data producer, the teams that create the data, and data consumers, the teams that use the data. Think of it like a contract between a landlord and a tenant. It sets clear rules for how things should work. Data contracts define the structure of the data, what fields are included, the format of the data, how the data is stored, and the rules for exchanging the data, how the data should be shared between the teams. Data contracts ensure that the data is of high quality and trusted. They have also help scale the system as the business grows. For example, if a new team wants to use the data, they can refer to the data contract to understand how to access and use it. Conclusion: to wrap up, the media and entertainment customer is modernizing its data architecture using cloud services like AWS and Snowflake. By creating a single source of truth and standardizing data ingestion and using tools like dbt and data contracts, they're making their data more accessible, reliable, and useful for the entire organization. If you're new to cloud computing, I hope this video helped you understand how data flows in a modern cloud environment. Thanks for watching, and I'll see you in the next session. Thank you. Today, I'm excited to take you through an incredible transformation journey, one that took a slow, outdated Postgres data warehouse and turned it into a high performance, real time analytics powerhouse on Snowflake. If you have ever worked with legacy systems that just can't keep up with modern data demands, you will definitely relate to this story. The company we work with, a major US delivery services provider, was struggling with frequent data outages, slow processing times, and the inability to scale. Their goal: a modern, automated, and real time data architecture that would empower their business users with instant insights. And that's exactly what we delivered with Snowflake. Let's dive in, starting with the challenges they faced. So, what was the real problem? Why did they need this migration? Well, their existing Postgres based data warehouse was simply not built for scale. Here were the key challenges. First, being high latency. Their data ingestion and processing took hours, sometimes even days. This meant business users were working with outdated reports instead of real time insights. Then there were frequent data outages. Their system kept crashing under heavy workloads. 90% of the failures were due to system downtime. Then there were a lot of manual interventions. ETL jobs required constant babysitting. Errors meant hours of troubleshooting and slowing down their operations. Also, another key thing was there was no CDC change data capture happening. Every time they needed an update, they had to refresh the entire tables instead of just processing new or changed data. And finally, there was slow third party data integration. Adding new data sources was a nightmare. Each new integration required custom scripts and weeks of effort. Clearly, their architecture was holding them back. Now let's look at what their system looked like before the migration. So their existing architecture had serious limitations. Let me kind of walk you through it. So the company relied on 20 plus different applications in-house RDBMS systems, but their ingestion was outdated, leading to longer delays. The ETL processing was in Postgres. So Postgres was not designed for high-speed, large-scale ETL workloads. The lack of real-time streaming meant batch processes frequently failed, further increasing the latency. And it also meant high maintenance costs. So running on-prem infrastructure meant huge operational costs. Teams were spending too much fixing failures rather than focusing on business insights. So as you can see, this architecture was monolithic. You had multiple data sources, and the data warehouse was on Postgres. Most of the ETL was done on Postgres, and this architecture was on-prem, and it was monolithic and inefficient. So this caused multiple operational as well as scalability issues. So clearly they needed a radical change. So we designed a future-proof cloud-native architecture that solved all these problems. So enter Snowflake, the fully automated, scalable, and high-performance data warehouse that transformed their analytics landscape. Let me walk you through the key components of the new architecture. As you can see from the diagram, so we implemented Fivetran to extract data from Postgres and move it to Amazon S3. This eliminated manual ingestion headaches. We used Kafka and AWS SNS to stream real-time events, enabling instant data movement. To handle third-party data sources, we integrated Segment API and custom connectors to ensure seamless data flow. And then we had automated processing in Snowflake. So once the data landed in S3, Snowpipe automatically picked it up and loaded it into Snowflake. No more waiting for batch processes. Business logic and transformations were handled natively within Snowflake, reducing complexity and improving performance. Then, for real time data streaming and change data capture, one of the biggest upgrades that was implemented was on the CDC aspect for this customer. So this was done using Kafka. This allowed us to process only modified records instead of refreshing full tables, making the systems faster and more efficient. And also, we kind of structured and processed the data into data marts, making it easily accessible for BI and data science teams. Business users could now generate real time dashboards in seconds. So this was how the future state architecture looked like. Now let's talk about how we made this migration happen. So migration of this scale required careful planning and execution. Here's how we did it. The first step was assessment and planning. We conducted a full audit of the existing system to identify dependencies and risks. We defined data governance policies to ensure data consistency. In the next step, we kind of figured out the incremental migration strategy. So we used Fivetran to replicate data from Postgres to S3. We implemented Kafka CDC to track real-time changes. And then on validation and testing, we compared the migrated data against legacy Postgres data to ensure data accuracy. And here, as part of automations, we developed automated scripts for data validation and consistency checks. And finally, in the last step, we decided on the final cutover and go live dates. So we switched to the Snowflake as the primary data warehouse here. And we kind of implemented automated monitoring and alerting for proactive issue resolution. And now for the big question, what impact this migration had for this customer? So the results were outstanding. Let's go over the key improvements. First being near real-time data availability. Data that previously took hours to refresh is now available in seconds or minutes. It led to 90% reduction in data outages. Automated ingestion and Snowflake's failure mechanisms virtually eliminated the data failures. We also implemented seamless change data capture. CDC processes now processes only the changes instead of the full table refreshes, cutting down processing time significantly. We also built fully automated and low maintenance pipelines. So Snowflake plus Fivetran plus Kafka reduce operational overhead. So there was no more need for manual interventions. This architecture also supported faster third-party data onboarding. New data sources now can be integrated in days instead of weeks. And finally, it also led to significant cost savings. With Snowflake's auto-scaling, the company optimized storage and compute costs while gaining infinite scalability. This migration didn't just improve their operations, it transformed their entire approach. Welcome to this case study on migrating and archiving ADAS workloads to AWS. The automotive industry is undergoing a digital transformation with advanced driver assistance systems, commonly referred to as ADAS, leading the way. ADAS includes features like lane departure warnings, adaptive cruise control, autonomous emergency braking. So these systems rely on massive amounts of sensor data, AI models, and real time processing. However, managing these workloads at scale is one of the biggest challenges for automotive manufacturers. That's where AWS comes in. So before we go deeper, let's define an important term, OEM. OEM stands for Original Equipment Manufacturer. In the automotive industry, an OEM refers to the major car manufacturers like Toyota, Ford, BMW, Tesla, and Volkswagen. They design and produce the entire vehicles. In this case study, our OEM is a leading automotive company developing ADAS technologies. But here's the challenge. ADAS systems generate terabytes of data daily from sensors, cameras, and simulations. Storing and processing this data on-prem is expensive and inefficient. The company needed a scalable and cost-effective solution for managing, storing, and archiving ADAS workloads. That's where AWS became the perfect solution. As automotive manufacturers develop advanced driver assistance systems, they face one of their biggest challenges. ADAS technology relies on real world driving data, high resolution camera feeds, LiDAR sensors, radar, and AI models, generating terabytes of data every day. Managing this data on prem was becoming increasingly difficult due to several key challenges. Let's explore them one by one. So, ADAS workloads include high data intensive tasks such as object detection, lane detection, and sensor fusion. These systems generate an large amount of data, terabytes per day from vehicles, test simulations, and real world road tests. On-prem storage could not keep up with this rapid data growth, leading to storage limitations, high costs, and slow processing times. A new approach was needed to handle this explosive data growth efficiently. Then we had limitations around data transfer. So one of the biggest obstacles in managing ADAS workloads was data transfer bottlenecks. ADAS data is often collected from remote testing sites such as proving grounds, on-road test vehicles, autonomous vehicle testing environments, but these locations lack high-speed internet connectivity, making it incredibly difficult to move large data sets to a centralized storage. Without a reliable and scalable data transfer solution, real-time data processing was nearly impossible. Next, let's talk about the cost, one of the biggest pain points. So ADAS data requires two types of storage: high performance active storage, which is used for real-time data processing and AI model training, and then it requires long-term archival storage required for regulatory compliance and historical model testing. Storing ADAS data on-prem was extremely expensive because high-performance storage is not cost-efficient for long-term archival needs. Expanding storage capacity required continuous hardware upgrades. Maintenance costs kept increasing as the data volumes grew exponentially. The OEM realized that their current infrastructure was financially unsustainable and needed a cost-effective alternative. Now that we have seen the challenges of managing ADAS workloads on-prem, let's talk about how AWS provided a scalable and efficient solution. The architecture is designed to ingest, store, archive, and process ADAS data using AWS services. Let's break it down step by step. Step 1: Data ingestion, moving ADAS data into AWS. The first step is getting the ADAS data into AWS. ADAS test sites generate massive amounts of data, and AWS provides two methods to move this data efficiently: AWS Snowball, offline transfer. So, AWS Snowball, this is a physical device used to transfer large volumes of data when internet connectivity is slow or unavailable. Data from ADAS test vehicles or legacy storage is copied onto Snowball, and the device is shipped to AWS for upload. This method is best for storing large data sets collected in remote locations. The second option is AWS Data Sync, which is for online transfer. This is a real-time data transfer service that moves ADAS data over the internet. It continuously syncs data from on-prem storage to AWS without manual effort. It is perfect for ongoing data collection from test vehicles and simulations. So, the first step is about moving the ADAS data into AWS, either offline using Snowball service or online using AWS Data Sync. The next step is storage in Amazon S3, which is the data hub. So once the data is in AWS, it needs to be securely stored and organized. AWS uses Amazon S3, which is the simple storage service to store the ADAS data effectively. S3 stores data in buckets, as you can see. Think of buckets as folders where all the ADAS data is organized. Data is tagged and categorized. This helps in quick retrieval and better data management. It is also highly scalable and secure. S3 can handle petabytes of data while keeping it protected. Now that the data is stored, let's see how we archive older data cost effectively. ADAS data doesn't need to be accessed all the time. Some of it needs to be archived for regulatory and compliance or historical analysis. AWS provides three storage tiers to manage costs effectively. The first is S3 standard storage tier. This is for frequently accessed data. S3 standard infrequent access, S3 IA, for data that is used occasionally. And then finally, we have S3 Glacier for long-term archiving at lower cost. For example, real-time ADAS data is stored in S3 standard for quick access. Older test results and simulations move to S3 standard IA. Regulatory data for compliance is archived in S3 Glacier for long-term retention. With this tiered approach, companies save money while keeping data accessible when needed. Now, once the data is stored in S3, the next step is processing it to generate insights. ADAS data includes sensor logs, video footage, AI training datasets, all of which must be clean, labeled, and analyzed. AWS automates this using multiple processing pipelines. KPI processing pipeline, it identifies the KPIs or the key performance indicators from ADAS test data. SL processing analyzes sensor logs to improve AI models. Labeling uses machine learning to tag objects in camera feeds automatically. And we have finally data quality checks ensures that only high quality data is used for model training. AWS processing pipelines enable faster automated data analysis, helping develop safer autonomous vehicles. Before fully migrating to AWS, the OEM needed to evaluate the best approach for migration. That is where AWS Migration Evaluator and DataSync Discovery Service come into the picture. Provided migration tools to assess which workloads move first, optimize the cost before shifting massive datasets, ensure a smooth transition with zero downtime. This step ensured that the migration was planned efficiently without affecting ongoing operations. So this AWS-based solution completely transformed how OEM handled ADAS workloads. AWS Snowball and DataSync enabled fast data ingestion. AWS S3 provided scalable and secure storage. S3 Glacier and tiered storage optimized long-term cost. And finally, automated processing pipelines improve the data insights. So the focus of this case study was to understand how the storage tier in S3 helped with the archival of ADAS data. And with that, we conclude this use case. See you in the next one. Thank you. Have you craved something so badly that you embarked on a journey across the city to satisfy that craving? Well, that's exactly what happened to me when I saw an overloaded, colorful milkshake on Instagram. But little did I know, my hunt for this milkshake would lead me to an aha moment about data mesh. Today, let's explore how a simple food code can help us understand this revolutionary data architecture. So, it had been a couple of weeks since I first heard about data mesh, and I couldn't stop wondering, would it make our data engineers' lives easier or more complicated? To grasp it, I needed a simple analogy. Then, standing in the food court, surrounded by different food outlets, it clicked. A data mesh is just like a food court. So, imagine this. A mall food court has multiple food outlets, each specializing in different cuisines. You have Indian, Italian, Chinese, and even dessert stalls. Now, think of a company's data architecture. Each business function, be it marketing, sales, support, is like an individual food outlet owning its specific type of data. Just like the mall management sets the hygiene standards, a data governance team ensures data security and compliance. The food court provides self-service infrastructure, a shared space with tables and services, just like a data mesh provides a platform for domains to host and manage their data independently. Now, let's rewind a bit and understand why data mesh is a game changer. Over time, data strategies have evolved. When we consider the 80s and 90s, centralized data warehouses stored everything in one place. Then, in the early 2000s, data lakes emerged, enabling large scale storage but still requiring centralized data management. And when we think of 2010s to the present, businesses need real time decentralized data access, leading to the concept of data mesh. Now, let's simplify data mesh using our food code analogy again. It has four key components. First, there is domain oriented data ownership. So each team manages its own data, just like food outlets manage their menus. Then there is self-service data infrastructure. The mall provides a common space and payment counters, just like a data mesh provides infrastructure for all the domains. Then we treat data as a product. So food courts serve dishes customers love. Similarly, domains produce high quality reusable data products. And then we have federated governance. So while food courts follow central hygiene regulations, domains follow common governance rules ensuring security and compliance. So let's say a retail company wants to implement a data mesh. Here's how it works. So the marketing team owns campaign performance data and shares it via a well-defined API. The sales team manages transactions and revenue data, making it accessible to finance. Support team logs customer interactions, which can be analyzed for customer experience improvements. So instead of having one central team handling everything, each department now owns and shares its data seamlessly. So by now you should have a solid understanding of data mesh and why it's a game changer for modern businesses. Just like my milkshake adventure, understanding data mesh takes curiosity and exploration. So the next time you are at a food court, think about data mesh and maybe grab a milkshake too. So in the subsequent sessions, we'll be seeing examples of data mesh implementations on AWS and Azure. Thanks for watching this session. Bye bye. Good morning, everyone. Today we are going to explore the fascinating world of data lakehouses, a revolutionary concept that combines the best of two approaches: the structured data governance of data warehouses and the flexibility of data lakes. Imagine it is early 2000s. Data was simple, structured, predictable, and orderly. Tables and rows reigned supreme. This was the golden age of enterprise data warehouse. But as businesses grew and diversified, so did their data. Suddenly, they faced a wave of complexity, new formats like JSON, images, and videos, all incompatible with these neat structured systems. Warehouses began to strain under the weight of evolution. Fast forward to the late 2010s, enter the data lakes, the disruptors, built on cloud platforms like AWS S3, Azure ADLS, and Google Cloud Storage. They offered something revolutionary: the ability to store everything. Structured data, check. Semi-structured data, no problem. Unstructured data, bring it on. It was a freedom at scale, but there was a catch: chaos, with no governance, no structure, and no performance guarantees. Data lake became dumping grounds, big, messy, with puddles of data everywhere. Now let's talk about the lakehouse era. Now picture this solution that blends the reliability of warehouses with the flexibility of lakes. Enter the hero we have been waiting for. The Lakehouse is a unified platform that scales effortlessly to handle petabytes of data, supports structured, semi-structured, and unstructured data, maintains governance, enabling BI, machine learning, and real-time insights. So the key takeaway here is the data lakehouse isn't just an evolution, it's a revolution. It's a single unified platform that empowers businesses to manage their data seamlessly, enabling smarter decisions, faster insights, and scalable innovation. So now let's unravel the inner workings of a data lakehouse, an elegant architecture designed to handle complexities of modern data. So the first stage, every story begins with raw material, and for a lakehouse, that raw material is your data source. So data flows in from diverse sources, structured like databases, semi-structured like JSON files, and unstructured like videos, images, or logs. So this is where tools like AWS DMS, Azure Data Factory, and GCP Dataflow come into the play. They act like pipelines, ensuring data is collected, transported, and deposited seamlessly. Third-party tools like Fivetran add flexibility, enabling quick integration across platforms. So the goal here is to bring everything in its raw, untamed form. Once the data is ingested, the data finds its home in a data lake, a scalable and cost-effective storage layer. Think of it as the foundation of your lakehouse. It is where all the raw data, structured, semi-structured, and unstructured, is securely stored. Depending on the cloud platform, you might use AWS S3, Azure ADLS, or Google Cloud Storage. Why is this stage critical? Because this is where scalability shines. The storage solutions handle petabytes of data without breaking a sweat. Next, we have the data transformation layer. Raw data is valuable, but refined data is priceless.
So this is where the data transformation comes into play. Using tools like Databricks, AWS Glue, or Snowpark, raw data is cleaned, enriched, and optimized. Prefer simplicity? No problem. Workflow-based tools like AWS Glue Studio or GCP Dataflow offer no-code solutions to streamline the transformations. At the end of this stage, your data is polished, ready to power analytics and machine learning. The final stage is where the magic happens. Turning data into insights, refined data is moved into a cloud data warehouse such as AWS Redshift, Azure Synapse, GCP BigQuery, or Snowflake. Here it is optimized for analytics, supporting massive parallel processing and real-time query. From this point, curated data becomes accessible for dashboards, machine learning models, and decision makers. Now that we have seen how Data Lakehouse works, let's address a critical question. What happens when your data is spread across multiple clouds? So when we think of the reality of today's enterprises, in today's world, many businesses do not rely on a single cloud provider. Instead, they adopt a multi-cloud strategy to avoid vendor lock-in, leverage the best features of platforms like AWS, Azure, GCP, and Snowflake, ensure flexibility and resilience in their architectures. But this brings its own set of challenges. How do you unify data when it is scattered across clouds? How do you ensure consistency and governance in a multi-cloud setup? The good news is that the data lakehouse architecture is platform agnostic. Regardless of where your data resides, the core lakehouse pattern, ingestion, storage, transformation, and warehousing remains the same. Here's how it works across multiple clouds. For centralized metadata and governance, tools like Databricks Unity Catalog or Snowflake Data Governance provide a single pane of glass to manage the metadata security and access controls and access clouds across all the cloud environments. Each of the cloud has native services like Glue, Data Factory, or GCP Dataflow that integrate seamlessly into the Lakehouse framework. So there is platform-specific integration. Next, we do also have cross-cloud connectivity. Many tools like dbt or Fivetran work across platforms, ensuring that ingestion and transformation workflows remain consistent. For unified data access, lakehouse architectures leverage open formats like Delta Lake, Parquet, or ORC, enabling interoperability across cloud environments. So the data lakehouse doesn't just unify data within a single cloud, it creates seamless bridge across multiple cloud platforms, enabling businesses to maximize value from their entire data ecosystem. Now let's dive into how this plays out on specific cloud platforms. We'll compare the tools and services provided by AWS, Azure, GCP, and Snowflake, showing how each platform supports the lakehouse architecture. Let's begin with AWS. So AWS offers a comprehensive set of tools that enable a robust lakehouse architecture. For data ingestion, we can use AWS DMS for migrating data from on-premise systems to the cloud. For real-time processing or streaming, tools like AWS Kinesis and Firehose come into play. For data lake storage, the foundation is AWS S3, a highly scalable and cost-effective storage service. AWS Lake Formation simplifies the governance and security. On data transformation, we can use AWS Glue for serverless ETL or EMR for Spark-based transformations. Workflow-based options like Glue Studio offer no-code capabilities. And finally, AWS Redshift can be used as a cloud data warehouse. AWS Redshift supports both structured and semi-structured data. Next, let's see how Azure Lakehouse can be implemented. Azure Lakehouse pattern leverages its tight integration across services. For data integration, we have Azure Data Factory for both batch and real-time ingestion. For real-time streams, we have Azure Stream Analytics is a powerful tool. Uh, on the data lake storage, Azure Data Lake Storage ADLS Gen 2 provides hierarchical storage for all data types. On data transformation, Spark-based transformations can be done with Azure Databricks, while Synapse Spark pools offer native options. No-code workflows can be built using ADF data flows. And finally, on the cloud data warehouse, Azure Synapse Analytics supports structured and semi-structured data along with massively parallel processing for large-scale analytics. Here's how you can deploy Lakehouse design using GCP. Google's Cloud Lakehouse model emphasizes simplicity and scalability. For data ingestion, we can use PubSub for real-time ingestion and GCP Dataflow for batch pipelines. BigQuery data transfer service supports seamless integration with SaaS applications. For the data lake storage, we can use Google Cloud Storage, acts as the scalable storage backbone. Spark-based transformations are handled by Dataproc, while dbt can be used for SQL-based transformations. Workflow-based options are available via Dataflow. And for the cloud data warehouse, we have BigQuery that excels in large-scale analytics with native support for semi-structured data formats like JSON. So Snowflake's unique strength lies in its ability to work across multiple clouds. Here's how a Snowflake Lakehouse would look like. On data ingestion side, we can use tools like Fivetron or Airbyte to ingest data into Snowflake or cloud storage. Depending on the underlying cloud storage, Snowflake integrates with AWS S3, Azure ADLS, or Google Cloud Storage. On the data transformation, we can use Snowpark. It enables Spark-like transformations with Python, SQL, or Java. Streaming transformations are supported with Snowpipe. And Snowflake supports structured and semi-structured data with variant data, enabling flexible queries across the data formats. So the cloud data warehouse layer would be on Snowflake. So each cloud platform offers unique strengths, but the Lakehouse architecture remains consistent. The choice of the platform depends on your organization's existing ecosystem, workloads, and business needs. But to sum it all, the Data Lakehouse is more than just a technical innovation. It's a philosophy for the future of data. It empowers businesses to unify data, unlock insights, and drive innovation across BI and ML use cases. Thank you for watching this session. If you have any questions, please feel free to reach out. Thank you.